Welcome to This Explainer. Today, we're uncovering the absolutely mind-bending reality behind extreme time dilation. We're using the sci-fi classic Interstellar and, actual hardcore astrophysics as our guides here. I am so excited to share this with you because we aren't just looking at Hollywood magic. No, we're looking at the foundational rules of our universe. So, let's just dive right in. To kick things off, let's ask the ultimate question based on that jaw-dropping movie premise. If you remember the film, the astronauts land on this wild water world where every single hour spent on the surface equals 7 years passing back on Earth. It's a devastating emotional hook for the characters, right? But we gotta ask, does established physics actually allow a time slip of that magnitude? Okay. Let's look at the numbers. That extreme conversion means we're dealing with a massive factor of 61,400. Basically, for every single second that passes on this fictional Miller's planet, 61,400 seconds pass on Earth. Actually, think about the intense musical score by Hans Zimmer during that scene. There's this distinct ticking sound in the background. Well, every mechanical tick you hear represents roughly 77,000 Earth seconds. That's about 21 hours. Every time you hear a tick, boom. Nearly a whole day has just vanished back home. Absolutely wild. To really understand how this works, we need to firmly distinguish between the two separate impacts of Einstein's theory of relativity. On one hand, we've got special relativity. This basically says that as an object moves faster, as its speed and acceleration ramp up, time actually slows down for that object compared to someone just standing still. Then, on the other hand, we have general relativity. This is the one that says massive objects literally warp the fabric of space-time itself. So the stronger the gravitational pull, the slower time passes. Now, for our scenario today, we're dealing almost entirely with that second one, the extreme gravity of a supermassive black hole. Let's see how this builds using a pretty brilliant thought experiment. We're going to trace the actual journey of light as it struggles to escape a massive black hole. Imagine person A is floating right near the event horizon, and person B is far, far away in deep space. Person A fires a green laser at person B. Now, green light vibrates at about 600 trillion times per second. But as that light climbs out of that intense gravity well, it has to expend massive amounts of energy. By the time it finally reaches person B, it's lost so much energy that its frequency has just plummeted to 10 billion vibrations per second. It isn't even green light anymore. It's literally a microwave radio beam. Now, what's really fascinating here is the core mechanic of what we call gravitational redshift. We just established that the light lost energy, right? But those missing light wiggles don't just vanish into thin air. Think about it. Person A absolutely created 600 trillion wiggles in 1 second. So if person B is only receiving 10 billion of them in a second, well, it proves that the very definition of a second is fundamentally different for both observers. Time itself is literally passing differently. So here is the absolutely crucial point. Both mechanical and biological clocks run at wildly different rates depending on their local gravity. To receive the 600 trillion wiggles that person A generated in a single second, person B has to sit around and wait 60,000 seconds. That's nearly a whole day. And yes, this applies to biological rhythms too. If person B pointed a telescope at person A, they wouldn't just see a redder light. They'd literally see person A's heart beating and their lungs taking a breath in excruciatingly slow motion, spaced days apart. Talk about the world's most boring staring contest. And this brilliantly illustrates how scaling up gravitational mass completely changes the flow of time in the universe. Right here on Earth, our gravity is pretty modest. We only experience a slowing of a few microseconds per day. If you visited the surface of our sun, which is obviously much more massive, you'd gain about 66 seconds per year compared to deep space. On a dense neutron star, time slows by a few hours per day. But at the surface of a black hole, the gravity is just so humongous that time is effectively slowed to a dead halt. Now, before we get completely lost in black holes and exotic physics, let's remember this is a very real everyday phenomenon. We literally have to use Einstein's equations to correct the clocks on the International Space Station right above our heads. Because the ISS is moving at high speeds and is slightly further away from Earth's gravity well, it operates on a slightly slower time reference than we do down here on the ground. It's just a tiny fraction of a second, but if we didn't mathematically correct for it, the global GPS systems on your phone would completely fail within a day. You literally wouldn't be able to navigate to the grocery store. But when it comes to the extreme math of Hollywood, we gotta consult Kip Thorne. He's the Nobel laureate theoretical physicist who acted as the science advisor and executive producer for Interstellar. From the very beginning of the project, Thorne laid down a strict rule with the film's director, Christopher Nolan. Nothing in the movie would violate well-established physical laws, period. If there was wild science fiction happening on screen, it had to spring organically from real, peer-reviewed science. Of course, when the movie came out, internet critics immediately jumped on the time dilation math. They argued that any planet close enough to a black hole to experience a 1 hour to 7-year time slip would have such intense gravity that it would just crush the astronauts under millions of tons of pressure. But remember Kip Thorne's rule. He actually did the math. Thorne calculated that if the black hole was spinning extremely fast, like close to the maximum possible spin allowed by physics, the innermost stable circular orbit actually shrinks. This rapid spin allows a planet to safely orbit close enough to get that massive time dilation without the local gravity squashing the humans on the surface. Pretty neat workaround, right? Thorne also expertly addressed critics of that massive, peaky ocean wave that crashes over the crew. Critics pointed out that a normal tidal bulge wouldn't look like a single towering wall of water. Well, Thorne explained it as a mathematically sound, solitary wave. See, because the planet is so close to the black hole, it's constantly being pulled and distorted. It hasn't perfectly locked its face to the black hole yet, so the planet physically swings back and forth in the gravity. That rocking motion generates a highly stable, non-breaking, solitary wave. It's actually a phenomenon first discovered by physicists in European water canals back in the 1700s, but here it's just scaled up to an apocalyptic cosmic level. As we wrap up this explainer, I think it's clear that the truth really is stranger and far more fascinating than fiction. By blending Einstein's actual equations with a compelling narrative, we get a profound glimpse into how the cosmos actually operates. But it leaves us with a huge question. As our technology advances, will humanity ever step out into the void and experience these extreme forces firsthand? Or will surviving the true nature of time and gravity forever remain beautifully calculated science fiction?